In this video, we're going to talk about relative strengths of conjugate pairs and the effects of salt solutions on pH. So let's get going with the conjugate pairs situation. So identifying conjugate acid and conjugate base from one or the other is a kind of necessary tool in this chapter. So let's take a look at a reaction with a weak acid with water. So the sort of quintessential weak acid in most examples is acetic acid plus H2O will give us acetate ion and H3O plus. Right? So acetic acid, here's our acid, and that makes the acetate ion the conjugate base. So if acetic acid is the acid, that means that water is the base, and hydronium ion is the conjugate acid. Now, the important thing to recognize here is that acetic acid is a weak acid, right? And acetic acid has a pKa of 4.74. Okay? The other acid in this equation is the conjugate acid, the hydronium ion, and it has a pKa of negative 1.7. So remember, smaller pKa is a stronger acid, right? Same thing goes for pKb, right? So pKa is related to the acid dissociation constant, pKb is the base dissociation constant. So pKa, lower pKa gives us a stronger acid, lower pKb means a stronger base. Okay, so let's take a look at the conjugate pairs. Okay, so comparing base strength from acid strength. Say, okay, so we're comparing H3O plus, which has a pKa of negative 1.7, versus acetic acid, which is a weak acid, with a pKa of 4.74. Right, so we're going to take a look at those acids, and then we're going to figure out what the bases are and compare the strengths of those. So the conjugate of H3O plus is H2O. All right, so these are our acids, and these are our bases. Right, so the conjugate of H3O plus is H2O, and the conjugate of the acetic acid is the acetate ion. So our question here is, which is stronger? Okay, so we have a number of different relationships that we can use to our advantage. So we've got one of those relationships is the relationship of pKa and pKb equals pKw. Right? Or we could use Ka and Kb. Ka times Kb equals Kw. Right? So if pKa for the hydronium ion equals minus 1.7, then 14 minus negative 1.7 equals 15.3, which is the pKb for H2O. And then our pKa for the acetate, or the, acetic acid, was 4.74. So 14 minus 4.74 gives us 9.26. As the pKb for the acetate ion. Right? So remember, lower pKa or lower pKb means that it's stronger. Right? So that means that between H2O and acetate ion, the acetate ion is a stronger base. Okay, so as a general practice, as a general idea, the conjugate of a strong acid will be a weaker base. We can say strong acid or strong base, so just conjugate of a strong is very, very, very weak. Okay? Whereas the conjugate of a weak something, acid or base, is stronger. Okay? So acknowledging that the conjugate of a weak acid is still a weak base. Okay? So that's still something that we have to keep in mind. Just because it's a weak acid doesn't make the conjugate a strong base. It's just stronger than the conjugate of a strong acid. Kind of a little bit confusing. Conjugate base of a weak acid is still in the weak category. Okay, but when we're comparing the conjugates of a strong acid versus a weak acid, the weak acid will have a stronger conjugate base than the conjugate base of the strong acid. Now the next topic is the effect of salt solutions on pH. Okay, and when we're talking about salt solutions, we're talking about ionic compounds. Okay, in other words, we need a metal. Remember, a defining characteristic of an ionic compound is the presence of a metal in the formula. Okay, so we're talking about things like sodium chloride or barium hydroxide. Right? Things of that nature, right? They're ionic compounds because they have a metal in the formula. Okay? So we just talked about the conjugates of strong things, okay? That the conjugate of a strong in this case a strong acid, is a very, with plenty of underlining, is a very weak base. Okay? But the conjugate of a weak acid or base is a good acid or base? Okay, so how do we determine what the effect is of a salt? Because we're not necessarily talking about acids or bases. So we can do a qualitative assessment of how a salt will affect pH, because they often do. Your strategy is to dissect the salt. Okay. What is the anion and what is the cation? Okay, so here are your rules. Here's how you can assess the effect of salt on pH. So 1, cations of group 1 and some of group 2 have no effect on pH. And I say some of group 2, and the ones that I'm specifically talking about are the heavy ones, the calcium, the strontium, and the barium. These are all 2 pluses. These all have no effect on pH. Okay? They're just spectators. Okay, and that's usually what group 1 metals are good for, is just balancing charge so that things can be. They don't generally tend to participate in things. Part 2, anions of strong acids okay, and we're talking about the strong acids from the list of strong acids, have no effect on pH. Okay, and actually I stepped over one particular thing. So going back to part 1, cations from group 1 and calcium, strontium, barium have no effect. All others make the solution acidic. Okay, and that means we're talking about things like iron, aluminum, things that are not group 1 calcium, strontium, barium. Okay, so if you have a cation in the solution that is not group 1 or calcium, strontium, barium, it's going to result in an acidic solution. Okay, number 2 says anions of strong acids have no effect on pH. Okay, and the reason for that is that strong acids, all they do is come apart. Okay, and we'll talk about how that plays out with affecting pH here in a second. And then number 3 is anions of weak acids are conjugate bases and make solutions basic. Okay, so cations that are not group 1 calcium, strontium, barium will make things acidic. Anions of strong acids have no effect, and anions of weak acids will make things basic. Okay, so let's talk about what I'm talking about. So if I take some HCl, let's change up the color here. So if I take some HCl and I put it in water, the only thing it does is come apart. And we get H3O plus and Cl minus. Okay, we have our acid, our base, our conjugate acid, and our conjugate base. Okay, in order for that chlorine, okay, so when we're talking about this is our anion of a strong, okay, or the conjugate of a strong acid. In order for that to have any effect, it needs to react with water. Okay, in order for that to have any effect, we are already making H3O plus. So in order for this to have any kind of action with water, we would need to have some sort of OH minus production, right? And this does not happen because it only comes apart. Okay, so we would have to have some sort of backward reaction with the chlorine and the water in order to produce hydroxide. And that's not going to happen because the strong acid only comes apart. Okay, so the anion of a strong has no effect on pH. Okay, other examples are any of the strong acids. We get H plus NO3 minus. Right, so you may see this in terms of potassium nitrate or sodium nitrate. Or calcium nitrate. Okay, and what I mean by take the salt apart, if I'm talking about calcium nitrate, I get calcium 2 plus and NO3 minus, right? Two of those, right? This one has no effect. And this one is conjugate of a strong, or the anion of a strong. No effect. Okay, so calcium nitrate as a salt will not affect pH. Okay, so let's talk about things that do affect pH. Right, so let's look at an example. For example, sodium acetate. Right, here's my salt. I've got sodium as a metal with an anion. If I dissect it, I get sodium plus and acetate ion. Right, so sodium is group 1, no effect. This is the conjugate of acetic acid. Right? So it's a conjugate base. pH will be basic. All right? Let's look at another example, NH4Cl, ammonium chloride. Right? We break that one apart and I get NH4 plus and chlorine minus. Ammonium is not group 1 or calcium, strontium, barium. This will result in acidic pH. And chlorine is the anion of a strong, no effect. Okay, so how this all works is a process called hydrolysis. Okay, and this is in the textbook in this section. So hydrolysis is defined as when an anion reacts with water, excuse me, not an anion, but just an ion. Could be cation or anion. Sorry, I misspoke that. When an ion reacts with water to make H plus or OH minus. Okay, so in our previous examples, we would say that NH4 plus hydrolyzes, excuse me, I'm not spelling that correctly, hydrolyzes water to make H plus. Okay, and acetate ion hydrolyzes water to make OH minus. And what do those equations look like? So all I have to do to show those equations is to take our cation or anion and put it with water. So if I have some NH4 plus H2O, my NH4 plus is going to donate to the water, so I'll have NH3 and H3O plus. Right, so the result is acidic conditions. My acetate ion, if I react that with water, it's going to make acetic acid, undissociated acetic acid, and some OH minus. Okay, so this is how hydrolyzation or hydrolysis works. Okay, and this is why our cations that are non-spectators result in acidic solutions, and why our anions of weak acids result in basic solutions. And that's going to do it for this video. We're going to come back with more evaluating acid-base strength in the next video, talking about how structure plays a part.